Are we ready? Cool. Okay, so well, since people seem to have a hard time understanding trivializations of bundle morphisms, I'm just going to go over that one more time before starting. So recall that a bundle morphism between two fiber bundles, E pi m and E prime pi prime m prime, is a pair of maps that maps the base manifolds through H and maps the bundles, the total space, through H tilde, such that this square commutes. So it's just smooth maps, a smooth map from M to M prime and a smooth map from E to E prime, such that it preserves the fibers. Now, suppose we assume that E and E prime have the same fiber. And suppose this bundle, the E pi M, has a bundle atlas given by U alpha and chi alpha, where the U alphas are open subsets of M that form a cover ring, and chi alphas are maps from E into U alpha across the fiber. Let me call this fiber F. And similarly, E prime, pi prime, M prime has atlas U beta prime and chi beta prime. So we want to figure out what these maps look like in these local trivializations. So as functions in terms of these chi alphas and chi betas. From just previous lectures on smooth manifolds, we know that for every such pair of open sets, H has a local representative from Rn to Rn, Rm to Rn, where M and N are the dimensions of these. So we can consider this following square, E prime with this map H tilde. We can, let's say we restrict E to some, we consider E over the open subset U alpha. So we have this trivialization chi alpha from E to U alpha cross F. Similarly, if we restrict this to beta, we have another trivialization here. So a local representative of this H tilde would be a map between these two sets. And because they're both Cartesian products, it's a pair of maps. The first map maps U alpha into U beta prime, and the second map maps an element of the fiber into an element of the fiber. Can anyone tell me what the first map would be, given that U alpha and U beta prime are subsets of M and M prime? Just H, or rather the local representative of H. So let me call that. Oh, right. So it's just H. Right. So H restricted to U alpha. It doesn't have to be the local representative because this is not a subset of Rm. It's a subset of the manifold. And so this is the only function that we need to determine from H tilde. And because it's a map from F to F, it's a smooth map from F to F, it has to be an element of the diffeomorphism group. So I'll call this map G alpha beta hat, where G alpha beta hat is a G valued function on U alpha beta, or diff F valued function on U alpha beta. And the fact that the square commutes is equivalent to saying that H tilde going this way of chi alpha inverse, let's say I consider a point P comma F in this, of chi alpha inverse of P comma F is equal to, going the other way, chi beta prime inverse of in the point in U beta prime is going to be H acting on P, and the point in F is going to be G hat alpha beta as a diffeomorphism acting on this fiber element. G hat alpha beta at the point P acting on F. So this equation just states that this square commutes. So it's a diffeomorphism. So it's a map from F to F. It's a smooth map that's invertible, so it's a diffeomorphism. Right. So G alpha beta hat is going to depend. The diffeomorphism is going to depend on which point in the open set U alpha you're on. So for each point in U alpha beta, there's going to be a map from F to F. So you can think of it you can think of the whole G hat alpha beta as a map from U alpha beta into diff F. Yeah, so just the diffeomorphism acting on a fiber element. So alternately, you can think of G hat alpha beta in this form. You can think of G hat alpha beta of P as an element of diff F, which means that G hat alpha beta of P is a diffeomorphism from F to F. Does that make sense? Yep. Okay. Yeah, maybe we can do this. Yeah. Yeah. Either way, it means the same thing as long as you get what that is. The notation doesn't really matter. Oh, yeah. Sorry. So X, there's way too many brackets here. X beta prime inverse acting on this element of the Cartesian product. That's what this means. Well, yeah, I don't, but then this becomes the prime and the inverse just become confusing. there's too many indices on X on chi, so I just had to figure out the simplest way to write that. Apparently there isn't one. All right, is this clear at this point? So this is in general when the structure groups of E and E prime are just diff of F. But we saw earlier that we can always, in terms of these local trivializations, if the transition functions take values in a subgroup of diff F or in some Lie group G, you can always reduce. You can reduce this. You can add more structure to this fiber bundle by ensuring that the structure group is G, which is some group smaller than diff of F. So if E and E prime both have a structure group G, then this map G hat alpha beta from F to F can be restricted to a G valued function on U alpha beta instead of diff F. Which essentially adds more structure to your fiber bundle and to your bundle morphisms. In that case, you just go back to diff of F. So if the structure groups are the same, you have this additional structure on bundle morphisms as well, which allows you to define this new category of smooth fiber bundles with structure group G. So the elements of this category are smooth FBs with cocycles or the transition functions that obey the cocycle condition in structure group G. And the morphisms between these smooth fiber bundles are going to be bundle morphisms that have local trivializations of this form. Yes, we are. Are we though? Can we in the category of smooth fiber bundles with structure group G, do we have to fix the fiber as well? No. Yeah. So it doesn't have to have the same fiber because every different sort of fiber will have some sort of G action on that fiber. So G hat alpha beta just takes takes values in G through the action on the fiber on E prime. Yeah, they can be different. All right. Mm-hmm. Yeah. So this can have any fibers. Mm-hmm. Yeah, I'm assuming F is the same over there. Yeah, at the definition of this category, you don't need the fiber bundle fibers to be the same. All right. Hmm? Yes. Exactly. So you can have a G action on the first fiber into the second fiber. That obeys the usual homomorphism rules. So it doesn't have to be an automorphism. It could be a map between two different fibers. Right?
Think of the fibers as having some extra structure, right? So let's say we will have later fibers that are vector spaces, or they might be alphas, rings, whatever. They have some extra structure on them. And then instead of defining smooth maps as just maps that are smooth on each fiber separately, you want them to also be morphisms in whatever category that the fiber belongs to, right? So we want those maps to preserve vector bundle structure, i.e. be linear, and stuff like that, right? So basically you replace arbitrary diffeomorphisms with homomorphisms in the category to which the fiber now belongs to.
So like if the fiber is a vector space, you replace them with just linear maps between vector spaces.
But like the structure that these fibers have, or the bundle has as total, is all really encoded in its structure.
So if you had, like, say, a line bundle and a plane bundle, and they both had, say, the translations of their structure group, so how would you define maps from one to the other? Just maybe there's a concrete example of that.
Oh, no, it's within one category, right? They have to be both vector bundles.
Yeah.
So like, in this case, like if you had, say, a line bundle with the structure group on the line being translations, and a plane bundle with the structure group on the plane being unidirectional translations, so the structure groups are isomorphic, could you define actions between them?
For sure, map one to the other. As long as the map is linear, that maps, right? The linear on the fiber. So it belongs to the set of morphisms on each fiber in the category of linear spaces, vector spaces.
And that defines maps from point on the line into points on the line into points of the plane.
But anyway, it'll be
All right.
more clear.
Yeah, when we get to vector bundles. All right. So like the end goal of studying fiber bundles is to be able to classify fiber bundles over arbitrary manifolds, which is one example of which we did last time when we classified all possible line bundles over the circle as either being the cylinder or the Mobius span. So we'll try and extend this a little bit further, and in order to do that, we can use a theorem called the homotopy lifting property, which will be the main goal of today. So to do that, first we define something called a pullback bundle. So let's say we have a smooth fiber bundle E by M. And we have some other manifold N and a smooth map F from N to M. And what we want to do is construct some sort of fiber bundle over N that by using this fiber bundle over E. And the way to do that, this fiber bundle is called the pullback bundle, denoted by F star of E. So E pulled back by F. You want some representative F tilde here and some projection pi prime such that this square commutes. And this can be constructed in one of three ways. If you think of the category of smooth manifolds, F star E is literally the pullback. The let me just write that down. F star E is literally the pullback E times N over M. And if you, yeah, that's why I'm going to define it again. If you remember what a pullback is, or if you don't, this is what a pullback is. It's the set of point E cross M N is defined as the set of points. Let's see, what's the best notation for this? P comma N in the Cartesian product E cross N, such that pi of P is equal to F of N. So those points in the Cartesian product of E and M that map into the same point on the base manifold. That's defined as the pullback in category theory, and that literally gives you the pullback bundle. The only thing we need to add over here is to ensure that there's a smooth structure on this set that makes the projection pi prime. Sorry, let me write this as PR2 as the projection onto the second component here. So we need to ensure that there's a smooth structure on this pullback that makes this projection onto the second component smooth submersion. And we can show that there exists a unique smooth submersion by the second construction.
You can explain what that equality means, right? If you look at the conditions, so pi of p has to be the same as f of n, that's basically saying that the fiber above n in the new bundle, right? That's the fiber above n, the new base space, is literally equal to the fiber above its p image. Its image p in n. Right? You take a point n in n, you map it to m by the map f, and then there's a fiber above that point m, right? And you literally take that fiber and just copy it over to n.
Yeah.
Right? And you do that for every point on n, you get fiber bundle. The only question is how do you glue them into a smooth fiber bundle? And that's just basically because you can show that this thing is an embedded manifold.
Right, of E cross N.
Product, yeah, the Cartesian product, and that the projection is a smooth submersion.
All right. An alternate way of defining this is, let's say the typical fiber of E is given by F. And you have transition functions P beta alpha from Q alpha beta into G for a structure group G that define this fiber bundle E. F star E will be a bundle with base N, fiber F, sorry. And all we need to define this as a smooth fiber bundle is transition functions on this bundle. And to define those transition functions, we simply write F star D alpha beta as maps from F inverse of U alpha beta. Since U alpha beta is an open subset of M, F inverse of U alpha beta is the preimage of that in N, which is an open subset of N, because F is continuous, into the structure group G. And the way we define that is F star T alpha beta is equivalent to T composed with F. So T alpha beta was a map from M into the structure group G, from U alpha beta, which is a subset of M, into the structure group G. To define transition functions on this fiber bundle, we need maps from open subsets of N into the same structure group, given maps from this into that structure group. So all we have to do is compose with F, which is what we've done here. So this is called the pullback of a function. And it's called a pullback because you're taking a function defined on M and pulling it back to a function defined on N through this map between N and M. All right. So this guarantees that the projection onto the second component will be a smooth submersion, and we have a smooth fiber bundle defined over N with base space N. And also note that the fiber of the two fiber bundles are identical, and so are the structure groups. Questions?
Yeah, so just as so the pullback can be used in association with charts in differential geometries, precisely one of these.
Yes.
Where your other manifolds just are.
Yes, exactly. All right. Any other questions?
We haven't defined pullback in general yet.
Yeah. But like we'll just literally use this definition for that. There was a different kind of pullback, but this is the same thing. This is the
Modified version of the Cartesian product, which is what pullback bundle is in categorical terms. But the pullback of a function is very much unrelated.
Yeah.
You know, it's a coincidence that it
turns out to be related. All right. So we now have a proposition. Well, a set of three propositions. F star E has a unique smooth structure that makes the projection onto the second component submersion, which we already saw. Secondly, all definitions give isomorphic bundles. And thirdly, this the fibered coproduct E star M of N cross M N is an embedded submanifold of the Cartesian product E cross N. I'm going to state this without proof. And move on to a couple of remarks. So let's say E is a trivial bundle over M. And F is one of those maps from N into M. Then F star E is trivial for all F if E is trivial. That is, if it is equal to M cross the fiber. And it's very easy to see that by just using these transition functions. If T alpha beta is a constant, the transition functions for the pullback bundle can also be made constant. All right. Secondly, suppose you have two fiber bundles with a pair of bundle morphisms between them. Then E is diffeomorphic to or isomorphic to the pullback of E prime over H. Can you see why? So if you have a pair of bundles with bundle morphisms H and H tilde, then E is going to be isomorphic to the pullback of E prime over H.
It's just like one of those universal constructions where you like are able to put like E star E prime, or sorry, H star E prime is like some universal object that you like map. You can map into E. Is it one of those?
I mean, the pullback bundle is a universal object. Because it's a fiber product of EN over M. But
so like any pullback is therefore isomorphic to this thing.
Right, but
Or you're
I'm asking if this bundle this fiber bundle E that is that obeys this bundle morphism is isomorphic to a pullback. So we can tell that there is a map from which to which for the fiber product. Is it a universal? Is the fiber product a universal uh, terminal point or initial point? Right. I forget what terminal and initial points are. Yeah, never mind. But
Oh, is this restricted to the case when the fibers are?
yes.
Okay.
But I mean, you don't really need to go into all that complication. Just given a bundle morphism, you can just look at the local representatives, the trivializations of the bundle morphisms, and then show that the transition functions of E are given by pullbacks of the transition functions of E prime. Once you do that, it becomes very clear to observe. Right. Mm-hmm.
So F star E is trivial if for all F. What do you mean for?
So is trivial irrespective of the function f if E is a trivial bundle?
Oh, I see. Just E is trivial means the other thing is trivial.
Yeah. Yeah.
Sure.
All right. All right. One more definition. Restriction of a fiber bundle. So let's say we have some immersed submanifold of M. Via the immersion I from S to M. And we have a bundle on M. We can use this bundle on M to define a bundle on S by directly using the pullback. And this pullback is called the restriction or the restricted bundle. And denoted by E restricted to S, defined as the pullback of E over the inclusion map or the immersion. Mhm.
From the sort of more crude construction, which is taking the local trivialization and taking basically slice tricks of them.
What sorts?
Or rather, basically taking the local trivializations and looking at their intersections with S and getting
Oh, I see.
S that way.
Yeah, just restrictions of those, because that's what I does. It's a so I mean that gives that once again I raise that, but that gives you the definition of the pullback of the transition functions on S, because it'll just be a restriction.
Just to generally give the pullbacks by an inclusion is the same as compositioning with the inclusion, which is the same
Right.
as restriction to the image of the inclusion.
Exactly. All right. Um, now we have a theorem for fiber bundles over sets of the form M cross I, where I is the interval 0 to 1. And the theorem states that every fiber bundle E by M cross I is isomorphic to the fiber bundle E naught cross I uh, over M cross I with pi naught cross identity, where E naught is the restriction of E to M cross 0 in this interval. And similarly, pi naught is pi restricted to, well, E naught. All right. And secondly, one sec. What is this? Never mind. Right. So I'm going to state this without proof because the proof is fairly technical, but it essentially involves taking this E naught cross I bundle and showing that every transition function on this can be split up into a transition function on patches on the interval I, and then those can be stitched together, glued together to make the transition function I constant.
This is intuitively saying that a non-trivial bundle is a bundle that has some twists in the fabric, like the Mobius band, right?
Yeah.
Going along the cycle. But the interval is contractible. So like intuitively, everything should be trivial along I. Right? And that's what this is saying. You can always choose the bundle atlas transition functions in such a way that they are
Like if you can that so that you can there won't be any twist over the interval as you go through the fibers.
that they are independent of the variable along I.
Yeah.
So like everything is constant along I.
So is this saying that essentially a fiber preserving homotopy can't do anything topologically interesting to the bundle?
Yeah, I think so.
Preserving homotopy for base space or some such?
Transition functions.
Yeah. We'll get there. All right. Questions? Cool. So we're skipping this proof. But in particular, a corollary of this proof is that continuous deformations or alternately homotopies of transition functions within the class of cocycles, so that the cocycle condition doesn't change, and you have within this homotopy class of cocycles doesn't change the isomorphism class of the fiber bundle. Can anyone see why this is true from the theorem?
there specific
Yeah, just deformations of the transition function in the as group valued functions. Think of what the definition of a homotopy between two functions is. You take the initial manifold, cross it with the identity map, and define a continuous map between. So let's say you have two functions f and g from m into m prime. A homotopy between these two functions is a map h from m cross I into m prime, such that when the element of I is 0, you get f, and when the element of I is 1, you get g. So essentially what you want to do is, given transition functions in this bundle, you already know that this bundle is isomorphic to this. So the transition functions in this bundle can be turned into transition functions in this bundle, which can then be viewed as transition functions t alpha beta as a function of a time variable t, where t takes values in I. And for each t, these are maps from, these are transition functions over over, well, u alpha beta subset of m into g, where g is the structure group of the fiber bundle e pi m. And these transition functions give you a homotopy between different transition functions of the same fiber bundle e to m. And that directly implies that homotopy continuous deformations of these transition functions just leave this fiber bundle invariant. They don't change the isomorphism class of the fiber bundle. Or rather, E naught. Yep. Mhm.
Say you map M across I down to I.
Okay.
And so treat M cross I as a fiber bundle over I. And then construct a map from E going down to I. So commutes. Is like a very small corollary of this, that basically E over I is always very boring. Literally true.
Yeah. Exactly.
I see. So all the information is sort of contained in M.
Yeah. But that's pretty much the point that Alex said that was used in proving that, because essentially any bundle over I is going to be trivial, because you can always you cannot create any sort of twists in the fiber over an interval. You can always choose transition function that'll make it constant.
But the proof is, you have to start with an arbitrary atlas, which is only over local patches that don't cover the entire I in that direction. And then you have to twist and modify the atlas by the lambdas, if you remember.
Yeah.
Transition functions that are defined all along I, right on a bigger patch, and are constant along I. So there's no transitions along I.
Any other questions? Okay. So now that we have all of this set up,
The meaning of this corollary is that if we want to classify fiber bundles
right.
let's say structure group, then we need to just ask, we need to classify co-cycles, i.e. sets of transition functions, up to homotopy.
Because homotopy equivalent transition functions would lead to the same isomorphism class of fiber bundles. So we're just slowly getting towards a better way to classify different isomorphism classes of fiber bundles.
So in the most abstract sense, that's what a characteristic class is.
Yeah.
It's just a homotopy class of co-cycle. It's helpful from the computational point of view. That's why usually people
Go to
always start
homology.
with different forms, other ways to represent characteristics.
Yeah.
A simple corollary is the evidence you can replace I with the disk, because I thought I had this corollary, but
I don't remember seeing that. Oh, that's a corollary of the homotopy lifting property. Yeah. I mean, how?
You M cross I is the same as M cross D too.
Um,
M cross I
wait.
cross I is D.
How is D2 I cross I?
In the sense that I squared.
Oh. Hmm.
By iterations. For all contractible spaces.
But like,
No. Just for I'm just talking.
I mean, M cross I is the same as N cross D2 for as a topological manifold, maybe, but not as a smooth manifold.
In rate of right? Replace D by I times I.
Right.
Take off one I at a time.
Right. But I mean, like this theorem holds for M cross I, but I'm not sure if that implies it holds for M cross D because this is for smooth manifold, right? Does this hold for topological manifold?
But they're different markers.
Wait, the square is not different.
Yeah. I mean, this.
Oh, right.
Oh, okay. All right. Yeah, I suppose. Yeah. Yeah. I mean, this would be E. I don't know, half or something. Yeah. Yeah, definitely. That definitely follows as a corollary of this. All right. So now the main theorem for today, the homotopy lifting property. Also known as the covering homotopy theorem. So this theorem states that suppose you have two fiber bundles E to M through pi and E prime, pi prime, M prime with the same fiber F. And suppose you have a pair of bundle morphisms between these two, or rather a bundle morphism, which is a pair of maps. Call them H naught and H naught tilde. And additionally, you have one more ingredient, which is a map from M cross I into M prime, which is a homotopy of H naught, hence the notation H naught, i.e. H restricted to M cross 0 is simply equivalent to H naught. We don't care what it is at 1. So just a homotopy that restricts to H naught initially at time 0. Then the conclusion is that there exists a covering of the homotopy H, which is a homotopy between M and M prime, by a bundle map E cross I, H tilde E prime. So essentially the statement being that this homotopy between M cross I and M prime can be lifted to a homotopy of the fiber bundles in such a way that this pair forms a bundle morphism. All right, and the proof of this is conceptually straightforward, but uses too much notation, so bear with me. So we know that given that this is a bundle morphism, there's an isomorphism between E and the pullback of E prime over H naught. So let that isomorphism be lambda from E into H naught star of E prime. And what lambda does is takes the point P in E and maps it. So remember that H naught star of E prime was viewed as a subset of the Cartesian product E prime cross M, right? So this maps P into that Cartesian product through H naught tilde of P comma pi of P, where this is an element of E prime, because P is an element in E and H naught tilde maps it to E prime, and pi maps it into M. So this belongs to E prime cross M. And we know that this belongs to the pullback because the point P maps into the same point in M prime through the commutativity of the square. Commutativity, I don't know. All right. So we know that lambda is a bundle isomorphism of two bundles over the same base manifold. This is pi. This is lambda going this way. We have lambda inverse. And this is pi prime. And so this is step one. Step two. Since we have this map from M cross I to M prime, we have another such commutative square. E prime, pi prime, M prime, H, M cross I. We have this diagram, and we can pull back E prime, now using H instead of H naught as we did previously. So we can define H star E prime. What is this map? Whatever, this is some map, I won't name it. And this is going to be, what do I call this? Whatever, I'm not gonna call it, I'll add numbers later on. All right, and we already know that since there's a fiber bundle over M cross I, it has to be isomorphic to a trivial bundle over M cross I. So in other words, there exists a bundle isomorphism phi from H star E prime into H naught star E prime cross I, because H star E prime restricted to I equals 0 is basically just H naught, which maps M cross 0 into M prime. E prime pulled back over H naught. This is from the previous theorem, such that phi takes in an element f comma x comma 0. Again, pullback is an element of the Cartesian product. So this is an element of E prime. This is an element of M cross I. So this whole thing is an element of E prime cross M cross I. This and this. And maps it to f comma x comma 0, where f comma x is an element of this. viewed as a Cartesian product E prime cross M. And this is an element of the interval. So the previous theorem guarantees that there's going to be an isomorphism of this type that is invertible. So the inverse will just take elements of this form into elements of this form. Okay. And finally, right. This is what it calls. This is PR1 and this is PR2. If you view this as a subset of the Cartesian product, this thing projects onto the first component, this one projects onto the second component. And so there's also this bundle morphism from this commutative square, PR1 from H star E prime into E prime. Of course, this is not an isomorphism because it only goes one way. We have three different morphisms, three different maps: lambda, phi, and PR1. What we want to do is, establish a bundle morphism between E cross I to E prime. And to do that, we compose these three functions in the following way. We define H tilde as a map from E cross I into H naught star times I using lambda cross identity, because lambda was a bundle isomorphism from E to H naught star of E prime. And on the second component, you just leave the time the same. Oh, sorry. And from this H naught star of E prime, we have a map from this into this, which is phi inverse, because phi is a bundle isomorphism. So map this using phi inverse into H star of E prime. And after that, we have this projection into E prime. Sorry, I don't have enough horizontal space to write this in a line. Using the projection onto the first component. So in terms of, I'll just write it there so that it's clear. So if I pick an element here, let's say P comma 0 in E cross I, this is given by the composition of all three of these maps. So it's PR1 composed with phi inverse times lambda cross I acting on P cross 0. So that'll give you, since lambda maps P into this double, this will be phi inverse acting on H naught tilde of P, comma pi of P, comma, identity leaves this number 0 as it is, so 0. Now we already know how phi inverse acts on this triple. So if f comma x comma 0 is sent to f comma this double, this is already of that form. So this is going to be projection onto the first component of, this is f. So that'll be H naught tilde of P, comma x comma 0, which is pi of P comma 0. And projection onto the first component just pulls out this. So this will be H naught tilde of P. All right. So what this tells you is that H tilde is an extension of our original H naught, the lift of the H naught, because H tilde acting at time 0 is identical to that. So this is a homotopy. So H tilde is a homotopy between E and E prime. That at time equal to 0 gives you H naught tilde. And we've proven this theorem. Between H naught tilde and something, whatever that is. Mhm.
Get a feel for the theorem.
Yeah.
You start with the morphism between bundles, and then you just continuously deform them to another one.
Yes.
And we're just proving we can do that, assuming we have a homotopy between
Right.
the manifold.
Right. So what you have is a morphism between bundles and a homotopy between the base spaces. All you're doing is taking that homotopy between the base spaces and lifting it to a homotopy between the total spaces.
And the claim is just that, like, at each step along the way, like for each E cross, 1/2, say,
Right.
you still have a fiber bundle.
Yes. So it's a sequence of bundle morphisms between E and E prime for each value of the interval I.
And the claim, and then the final bundle that you have is it's not only just it doesn't only map into E prime, it maps in a way such that it like in a continuously connected way from the original thing.
Right.
And that's like the whole.
Right. Exactly. Exactly. So, I mean, we'll use this shortly in a bunch of corollaries next. But essentially, this you can, in some sense, think of this as an extension of the path lifting property that we looked at the last time. This reduces to the path lifting property if you consider M and M prime as just single points, which would be the initial values of the path.
M is a single point.
Not M prime.
M prime is the base manifold of the.
Oh, I see. Right. So if you think of M as a single point, which is the initial point of the path, and M prime as the base manifold or the covering space, this thing becomes a path into that manifold. And what this tells you is that the path in the manifold can be lifted to a path into the covering space or the fiber bundle. Except that in the case of the path lifting property, there's some additional conditions that ensure that the lifted path is unique. But in this case, this lifted homotopy is not unique. You can have multiple different homotopies that obey the same condition. Questions?
All fiber vibrations are actually defined using here instead we derived it for.
Okay, so wow, I still have an hour remaining. Might finish early today. A bunch of corollaries of this homotopy lifting property. Firstly, if E prime, pi prime, M prime is a fiber bundle, and F and G from M to M prime are smooth homotopic maps, then because these are both maps from M to M prime, you can use either of these to pull back E prime. So you have two bundles over M. You have F star E prime and F star G star E prime, pull back over F and pull back over G. And these are both going to be isomorphic. Can anyone see why? Lift from M to M prime. think of how you'd create an isomorphism over between these two bundles, given that you have a homotopy between F and G.
Rather, which map should you apply the theorem to?
Yeah.
With which map should we pull back E prime by?
Yeah. Any ideas? All right, I'll just tell you the answer. So because F and G are homotopic, there exists a homotopy H between M cross I into M prime. Exactly. Such that H of H restricted to M cross 0 is equal to F, and H restricted to M cross 1 is equal to G. And then we can pull back E prime over this H. So we get a bundle P, which I'll call H star of E prime over M cross I. All right. So, and obviously this is going to be isomorphic to some H naught star E prime cross I by our previous theorem. Now, in particular, consider the restriction.
We already know it's a trivial bundle over the I, right?
Yeah, exactly.
Where the last fiber is isomorphic to the first fiber.
Right.
And those are similarly F star E prime.
Exactly. So like define PT as the restriction of P to M cross T in the interval. P0 is F star E prime. P1 is G star E prime. And they're both isomorphic to each other by our earlier theorem. Okay. Second part of the corollary. Fiber bundles over contractible spaces are trivial. Why is that? Exactly. So like every contractible space is homotopically equivalent to a point, so the corresponding bundles are going to be isomorphic, and every bundle over a point is just trivial. It's the point times the fiber. All right, and finally, some more classifications of fiber bundles. Yeah, I'm definitely going to end early. Hmm? What? Sure. The most important result of today, isomorphism classes of, this is a long statement, fiber bundles with some given fiber F and structure group G over the n sphere instead of the one-dimensional sphere like we did last time, n greater than equal to 1 are in 1-to-1 correspondence with homotopy classes of maps from S n minus 1 to the connected component G naught of the identity in G. Still some more words. up to conjugation by the group of connected components of G. Or in equations, the category fiber bundles over Sn with fiber F and group G is isomorphic to bijective to the space of the homotopy classes of maps from Sn minus 1 to G mod pi naught of G, which is the group of connected components. The homotopy classes of these maps are simply the n minus 1th fundamental group. Well, n minus 1th homotopy group. The fundamental group is the first homotopy group. Mod pi naught of G. By the way, this mod is pi naught of G may not be a normal subgroup of this. So this mod is this quotient is quotienting under the action an action of pi naught of G on this group. It's not the coset space. All right.
So forget about pi naught of G. Let's say G is connected.
Yeah.
Anyone give an intuitive idea for why bundles of, let's say, two square classified by G value functions on a circle?
Is this something which will eventually be motivated by weakly optical correspondence, or?
Let's say, so you have this sphere, right? You want to classify all possible G values above it. How's that done? When you bundle, you glue all the distributed pieces by condition functions. How can you glue a bundle of those? How many pieces do you need? Overlapping along what?
Yeah. So
yeah. So all that matters is the transition function on the equation, which is a G value function. And we now know that that matters only up to homotopy.
So just homotopy classes.
Over the two sphere is classified by the homotopy class of a G value function on the circle on the equation.
Oh.
And so you have a bundle over the two sphere, let's say, right? You can break it up into two hemispheres. Every hemisphere is contracted out. So the bundle is trivial over the top hemisphere, over the bottom hemisphere. And then you have a transition function along the equator, right, on the overlap of the two hemispheres. Right. And that transition function completely classifies the bundle. But we now know that the transition function actually matters only up to homotopy. If you deform it by homotopy, it will not change the isomorphism class of the bundle. Right. So bundles are classified by isomorphism classes of G-value functions on the equator, which is a circle, Sn minus 1.
And so maybe this is just but so the reason we only have to do it on the circle is because we can think of the overlap as the circle times intersection.
Yeah.
And then we get triviality.
Yeah. Exactly. Okay.
Why is there this correction with the conjugation by analogy?
Well, because the circle.
If the group is not connected.
Because the circle or the your equatorial script is connected, so you can only see the one connected component.
Sure. So
yeah.
What? So I'm saying that there are actually fewer isomorphism classes than what I just said, right, for general groups. Well, remember what isomorphic bundles look like in terms of transitions. How do they change?
So we can conjugate,
Exactly.
Yeah, I have one lambda, some g-value function on the upper hemisphere, and another g-value function on the lower hemisphere. And I take my transition function multiplied by lambda inverse and lambda on the other side.
So we can always somehow transform it to the identity connected component.
Those will be isomorphic.
Exactly.
Yeah, so what if
Exactly.
the question is, what if these lambdas belong not to the connected component of the identity, but to some other connected component of the group? Right? Then the claim is that it's still an isomorphic bundle, obviously, because we use the lambda action, right? But it's not a homotopic map. The transitional function is not homotopic because it now takes values in a different connected component.
Okay, so then you can take your two charts and just shoot point and then conjugate it, transform everything by the inverse of the particular g value at that point.
Yeah. All right. Let me write down the proof in words, and it'll become a little more clear. All right. So the proof is, so we need first.
By the way, just
Mhm.
to be careful with the notation, FBSN, what that means is not literally FB is equal to, but the skeleton of whatever, the isomorphism classes, the set of isomorphism.
Right.
Not the set of fiber bundle.
Yeah, that would be. Right. Yeah. So we first need to start with an atlas for the n sphere, and so we already know that every n sphere is going to have two hemi n spheres. So we cover Sn by two hemispheres. Um, we call them U plus and minus that overlap in neighborhood of the equator. Let me call this neighborhood U naught of the equator. I'll call that C. And the equator is going to be isomorphic to Sn minus 1 because that's just the general property of an n sphere. So U naught is isomorphic. Mm-hmm. Yeah. So this neighborhood of the equator is isomorphic to Sn minus 1 cross some open interval. Let me call that minus 1 to 1. And we have only one transition function. I'll call that tau from U naught into G, where G is the structure group of the fiber bundle. Um, so case one, and all we have to do is specify tau to specify the isomorphism class of this. Specify tau to specify a fiber bundle, and look at isomorphism classes of tau, which is up to conjugation. So case one, suppose we choose tau such that tau of some point x naught is equal to the identity in G, where x naught belongs to the equator.
So we can essentially modify either of our charts by conjugating by g-value function.
Not conjugation, just multiply.
Oh yeah, sorry.
Yeah.
Composing with something.
Yeah,
So we
exactly.
just choose one compose with its inverse,
Exactly.
and then we'll have an identity somewhere.
Exactly.
So you can always fix the value of the transition function at one point to be anything
All right. So we choose tau such that at some point on the equator it becomes identity, and we define restriction theta as tau restricted to the equator. This restriction is called the clutching function. And essentially homotopy classes of this clustering function is what we'll see will give isomorphism classes of the fiber bundle. Now, what we need to do is consider isomorphism classes of these transition functions and show that they result in homotopy classes of theta. So let's say we have two transition functions, tau1 and tau2, such that the resulting fiber bundles are isomorphic. Yes, at the same point x naught. Such that, actually, yeah. Do they have? Yeah, sure. Yeah, we'll assume they turn into identity at the same point x naught. So such that tau2 is given by some conjugation, lambda plus tau1, lambda minus inverse, where lambda plus minus are maps from u plus minus into g. Remember from last lecture that we saw that if two sets of transition functions are conjugations of one another, the resulting fiber bundles are isomorphic. So these transition functions tau1 and tau2 result in the same isomorphism class of fiber bundles over Sn. No, so it was tau t. Yeah, sorry, not a conjugation, but t alpha beta 2 equals lambda alpha t alpha beta 1 lambda beta inverse. Yeah. All right. Now, actually, sorry. This is something we can always do, so we make sure that we do that, and we consider case 1, the case where lambda plus minus of x naught is identity. Now, in this case, lambda plus minus, because they're smooth maps from u plus minus into g, they all take values in the connected component of identity, which is g naught, right? And equivalently, we can deform lambda plus by homotopy so that lambda plus of the north pole, p plus. What's that?
Oh, okay. So these things extend into their respective patches.
Yeah, they're defined on the patches. So we can deform lambda plus by homotopy so that lambda plus becomes identity on the north pole, in which case it won't be identity anymore on x naught. It may or may not be. And similarly, deform lambda minus by homotopy so that lambda minus of the south pole is equal to the identity. All right. Now we'll pick coordinates on our open covering, on each patch of our open covering. So U plus is isomorphic to the n ball, which is a subset of Rn. And similarly, U minus is isomorphic to the n ball, which is also a subset of Rn, or diffeomorphic. So in this subset, using this subset characteristic, we'll establish Cartesian coordinates on U plus and Cartesian coordinates on U minus. Yes, around the north and south poles. So in U plus, we'll assume that the north pole is the origin. In U minus, the south pole is the origin. Let me just write that down. P minus corresponds to x minus equal to 0. And introduce the homotopy lambda plus of dx plus tau 1. Wait, so I'm a little confused. Let x be the, so let's say we pick a point x in, what's it called? In U0, which is the neighborhood of the equator. And x plus and x minus are coordinates for x. And consider this homotopy lambda plus of tx plus tau 1 of x, lambda minus of tx minus. Because this is in the intersection, you can have both coordinates for that point. So when we take t to 0, this quantity, the argument of lambda plus goes to 0, which means lambda plus goes to the north pole. When we take t to 0, this quantity also goes to 0, which means that the coordinates of this point go to the origin in u minus, which is the south pole. And we've deformed lambda plus and lambda minus such that they're identity at the north and south pole. So at t equal to 0, this is just tau 1 of x. And at t is equal to 1, x plus and x minus correspond to the same point. They're just different coordinates for that. So this is just lambda plus of x, tau 1 of x, lambda minus of x, which by our definition is tau 2. So given two isomorphic transition functions in the fiber bundle, we've constructed a homotopy that connects them. So we know that homotopy classes of, so we concluded that homotopy classes of transition functions result on the equator, or equivalently homotopy classes of the clutching function result in isomorphic fiber bundles, result in non-isomorphic fiber bundles. Right. Well, that's just the contrapositive of this. All right. So this was case 1 when we could make the lambdas go to identity on the equator. In the second case, let's say lambda plus of x naught and lambda minus of x naught are equal to some g naught. They have to be the same because tau 1 and tau 2 are both restricted to be identity at x naught. So in this case, where g naught does not belong to the connected component of the identity, it belongs to some other component. In this case, we can always deform, once again, lambda plus and minus so that at the corresponding poles, t plus and t minus, this becomes g naught. And exactly follow the same argument once again by setting up Cartesian coordinates and come up with a homotopy between tau 1 and tau 2. So we can do this for every single up to conjugation. Yeah.
Only it also doesn't matter what G naught is within that connected component, right?
Exactly.
G naught or anything within the connected component. There's a path connecting G naught to the other G naught. That you construct the homotopy from one transition to the other. So all that matters is the connected component itself and conjugating by it, which is a well-defined operation up to homotopy.
So we show that different homotopy classes of the clutching function up to conjugation by the connected components of the structure group are in one-to-one correspondence with what's it called? With different isomorphism classes of fiber bundles of arbitrary fiber over Sn. All right, and that essentially completes the proof. Any questions?
This is stated without proof in chapter 13 of Green Schwartz Whitman.
You finally got there.
No, don't talk about anything. They just say the SN and the SN minus one thing and don't talk about anything that's subtlety.
Obviously. Yeah. Spontaneous symmetry breaking to simple connectedness. All right. So let's look at some examples. So last time we proved that line bundles over S1 can only be in one of two isomorphism classes. Now we look at arbitrary vector bundles over S1 of rank K. The rank of a vector bundle is the dimension of its typical fiber. So the structure group in this case, because there's a vector bundle, we'll only look at linear maps between the fibers. So the structure group will be reduced to GLK of R, assuming real vector bundles.
We just start maybe if we just start with a vector bundle, or sorry, we start with a fiber bundle whose fibers are vector spaces. We could have nonlinear transformations.
Sure. Like,
General fiber bundles doesn't have to be.
yeah.
But let's say we restrict it.
Yeah. So this has two connected components.
So there's more isomorphism classes, the smaller your, in principle, more isomorphism classes, the smaller the structure group is.
Right.
Because there's fewer bundle maps with a more restricted.
So there's two connected components here from, actually, let me write that formula again. So FB is N F comma G is bijective with pi n minus 1 of G mod conjugation by pi naught of G.
But actually, you can show that when the fiber is RK, when the fiber is just a vector space, RK,
Mm-hmm.
the group diff of RK, of all diffeomorphisms of RK, is homotopy equivalent
To, yeah.
So there's no need in all of that infinite dimensional
Yep. All right. So we have two connected components. From that formula, we want to look at pi 0 of GLKR, mod pi 0 of GLKR, but that quotienting is by conjugation. And because conjugation happens with two elements of the same group, that conjugation is always acts trivially. So like if you conjugate with a determinant positive quantity, you'll still get the same thing. You'll still be in the same component, and if you conjugate with a determinant negative group element, you'll again still be in the same connected component. So fiber bundles over S1 with fiber the VK whatever RK are isomorphic to just pi 0 of no. You can't have a determinant 0.
Oh, you can't have determinant.
Invertible.
Oh.
So pi 0 of GLK R, which is equal to Z2. So again, you can only have two different isomorphism classes of vector bundles over S1. The same goes for line bundles as well. Do you have a question?
So what is the definition for the vector bundle?
Just the typical fiber is a vector space, is RK. and the structure group is GLKR.
So it is that your fiber is RK.
Yeah. The fiber is RK and the structure group is
I mean,
linear transformations.
actually more, but at this point it doesn't matter because all we're doing is just classifying all bundles. Fibers are K.
Yeah.
And the structure group is G.
Exactly. All right. Example number 2. We had R1 bundles over S1, and now we'll do R2 bundles over S2.
By the way, why was there no quotient thing by phi naught in this example?
I already mentioned that. Yeah.
Why?
Because conjugation by a determinant positive or determinant negative element brings you back to the same component.
Also because conjugation
Wait. Oh, no, I mean, I was thinking about GLKR. Like, you can always reduce this to Z2 because you're only looking at connected components. And then it's trivial. All right. So, plain bundles over S2. Once again, the structure group is GL to R, which has 2 connected components.
So if you have a general vector bundle with the sphere, then what this essentially says is going around the sphere can either keep the vector bundle just a linear transformation or and have a total linear transformation.
Wait, can you say that again?
Or basically, so going around the circle can either preserve your orientation or flip it.
Yeah, exactly. Exactly. So fiber bundles over S2 with fiber R2 isomorphic to pi 1 of GL2R mod pi 0. I'm not going to write GL2R again, which is the same as Z mod Z2, which is natural numbers. So Z2 acts on Z by.
Why is phi 1 of GL2?
You can just describe the transformation as like an element of the plane with a thing missing in the middle, right?
This deformation retract of O2. Homotopy equivalent to O2, basically. Or
Up to, yeah. So think of hiding. Right.
Exactly. Well, it's rotating and expanding or contracting, and you just can't send it to Z. It's like
exactly.
So the expansion and contraction that doesn't matter for homotopy classes, right? That you can deformation retract onto orthogonal matrices. And then it's O2. But phi 1 of O2 is the same as phi 1 of SO2. And SO2 is this one.
Okay, so it's just a winding of the sphere.
Exactly. All right. Another example.
Wait, why does Z2 act that way?
Connected components.
So the question is, how does orientation flipping on the plane act on these loops by conjugation? So imagine rotating the plane continuously through 2 pi, full rotation. Think of it as a continuous process. And then do a reflection of the plane along the y-axis, let's say, right? Then do the rotation by plus 2 pi, then reflect back. But you get the end result is what?
this is the standard dihedral group thing.
Yeah, rotation by minus 2 pi. So this conjugation flips the sign of the winding number. But apparently those 2 bundles would be isomorphic.
Yep.
Those 2 plane bundles.
As real vector bundles. When you get to complex, they won't be anymore. Another example, S1 bundles over S2. And we saw an example of this, which was the Hopf bundle, or the qubit bundle. The structure group is diffeomorphisms of S1, which is what's the symbol for homotopy equivalence? Is it just a tilde or tilde with a line?
Tilde and one line.
All right, which is homotopy equivalent to O2, which is isomorphic to S1 disjoint union S1, because it has two connected components, SO2 and SO2 with inversion, and each SO2 is just U1, which is a circle. All right, so fiber bundles over S2 with fiber S1 and structure group O2 are isomorphic, bijective to pi1 of O2 mod pi0 of O2, which is once again Z mod Z2, which is natural numbers. Essentially the same argument as for the plane bundles over S2.
And given the plane bundle of this here, by the way, he has a circle in yeah, just cut out the unit circle out of each type. Well, assuming that the transition functions map
Yeah.
It's a good analogy.
Yeah. Like math is trivial if you do it intelligently. All right. I like that definition. All right. So this was if we don't take into account oriented bundles, if we want to make sure that the fibers, the S1 fibers over S2 are oriented. So as in if we want to distinguish between an orientation one way and an orientation another way, we can reduce the structure group further down to SO2. So if we consider only orientation preserving diffs, O2 reduces down to SO2, and fiber bundles over S2, which is isomorphic to U1, with fiber S1 and structure group U1 are classified by pi1 of U1 mod pi0 of U1. This is trivial. This is just integers. And the corresponding element of Z for this bundle is called the Chern number. Which is our first concrete example of a characteristic class. Oh, so in this case, we didn't care about whether the diffeomorphisms preserved the orientation of S1 or R2 or reversed it. Yeah.
So like there we didn't care if the orientations of fibers matched on different hemispheres or not. Which is when it gave us more freedom to produce isomorphic bundles. You could like flip the orientation on one hemisphere, it would give you an isomorphic bundle. But now you're not allowed to do that. Let's say we restrict our structure group only to SO2, right? So we distinguish between orientation reversing isomorphisms and orientation preserving ones. Then there's more isomorphism classes, things like take twice more.
Yeah.
And now bundles are classified by integers.
Instead of just non-negative integers.
Winding numbers of the U1 valued function on the sort on the equation.
Wait, is that I just missed the setup here. Is that what the setup was?
Yeah. Yeah, no, that is the setup.
Okay.
So now we consider, instead of this, we consider specifically orientation preserving transition functions, and then our isomorphism classes of fiber bundles over S2 increases into Z, and the number that characterizes this isomorphism class is called the Chern number of the fiber bundle. Do you have a question? Oh, okay.
Only there's still one ambiguity with the sign system.
Yeah.
It's not clear which bundle we should assign plus one.
Right.
Wait. The turn number is what we care about, right?
No, in the integer. What I'm saying.
What element of V2 is called the turn number?
Oops. My bad.
Oh, okay. Yeah.
It's a winding number of the map from the circle into the circle. But which one do you assign plus one to?
Right.
So in real life, there's more structure to these bundles than what there is right now. Basically, the complex structure.
That's ironic because you said in real life there's
Yeah,
complex
that
structure.
has an orientation built into it, which is why we know what plus one actually means.
Yeah.
But at this level, we don't.
All right. So applying this to the hop bundle, we'll see what the churn number of a hop bundle is. So remember that this was an S1 fibration over S2 with the total space being an S3. And the way we did that was we considered a qubit state, which was a pair of complex numbers, alpha comma beta, normalization implied that mod alpha squared plus mod beta squared equals 1, which means that we have a 3-sphere in C2, which is the same as R4, and then global phase implies that alpha comma beta is to be identified with e to the I theta alpha, e to the I theta beta, and this gave us the block sphere S2. And since this global phase is an S1, we get this Hopf bundle. So let's try and see what the churn number of this Hopf bundle is. So we cover the base S2 with 2 disks. Or rather the hemispheres. D plus minus, which overlap at the equator and equator only. So they have their boundaries as the equator. Now, restrict the Hopf fibration S3, S2, S1 to these disks, right? And because the disks are contractible spaces, this restriction of the Hopf fibration is going to be a trivial fibration. So, so this is going to be diffeomorphic to D plus minus cross S1. So think about what this is. There's a disk times a circle. So I take a filled-in circle and rotate it around itself, which gives me a torus, a solid torus. In R3. Right? Does that make sense? So essentially what this means is that the S3 that we had can be written as the 2 disjoint solid tori, one each for D plus and one for D plus and one for D minus. And then we can glue the boundaries of this solid tori together, which are the boundaries of this disk, to get an S2, to get an S1 vibration over S2.
If you take a solid torus in 3 dimensions, you need its complement, right? If you think of the complement, it's also a solid torus. Only you need to attach the infinity as small to complexify it, and then it's a sphere.
Right.
The complement of solid torus in the projective space.
Attach the infinity to make it a 3 sphere as opposed to a 3 sphere.
Yeah. Just remember that the three sphere is just R3 with a point at the infinity. All the infinities put into one
The
point.
specific way to break it up would correspond to the trivial S1 bundle over the sphere. Whereas we need to take these two solid tori and glue their boundaries, not as you would usually do, just like
Exactly.
but do some twists to the boundaries of the tori and then glue them. And then you get S3, but corresponding to a different vibration.
Right. So essentially, let me write that down.
And the number of those twists is different.
By twist, that essentially gives us the fundamental
I mean, you take the solid quartz, cut it, right, so it becomes a cylinder. And then you twist the two discs relative to each other by some number of sides. Then what happens to the fibers, which are these circles that went like that inside of the torus, they now twist it up. They go like that around the torus.
Can we also twist the other S1?
There's no use, it's going to be a nice one. So then you do that twist, then you glue to the outer torus. And the vibration is still the same. You cut it by cross section and you project these deformed circles onto whatever the point is. In that cross section at the intercept. But these circles are now twisting around the torus.
Right. So in particular, if you want to look at the Hopf bundle, we want to figure out how these boundary tori twist as you glue them. So we go back to those qubit coordinates. Psi is two complex numbers, alpha, beta. We define the bundle restricted to D plus as the space of points with mod alpha greater than or equal to mod beta. Also, we remember that we still have mod alpha squared plus mod beta squared greater than or equal to 1. Oh, what is wrong with me? E restricted to D minus is the opposite of this. Those points with mod alpha less than or equal to mod beta. And obviously, the E restricted to the equator S1, or let me call the equator C again, is going to be, what is it going to be? Mod alpha is equal to mod beta is equal to half. 1 over square root 2. Yes. All right. Exactly. So so this gives us two angular variables that determine alpha and beta, and that's how we know that this is isomorphic to torus S1 cross S1. We define phi as a neutral coordinate on S2, and psi as the angular coordinate on the S1 fiber of the S2. So then with these definitions, we have E restricted to C is given by the sets of points alpha comma beta, given by the formula 1 over square root 2, e to the I phi by 2 plus I psi, comma e to the minus I phi by 2 plus I psi. And then we identify, so now we already have coordinates on the equator, we need coordinates on the disks. So we identify D plus minus.
Can you write out the projection
The what?
Projection.
Oh, pi of alpha comma beta is equal to mod alpha squared minus mod beta squared comma 2 alpha beta star.
Right. So if you look at the final these coordinates on the equator, when you plug it into that formula, you can see that it gets mapped to a point on the equator with the azimuthal coordinate equal to pi.
Yeah.
That
So
is the place.
essentially, this is an element of R. This is an element of the unit disk in the complex plane. And this R is so that when you enforce mod alpha squared plus mod beta squared is equal to 1, this projection becomes so that this disk sort of contracts as you increase or decrease this value. So as you increase, at this point, let me call this gamma. So this unit disk corresponds to gamma equal to 0. As you increase gamma up to 1, this disk contracts into something smaller and eventually vanishes at a point. Similarly, as you increase gamma to -1, it contracts down to a point as well. So this is how this projection gives you a two-sphere. All right.
And so if you plug in that number, e to the I5 or 2 plus I psi, e to the minus I5 or 2 plus I psi, that immediately gets 0 comma e to the I5, which is at the boundary of the disk in the center
Right.
of the equator.
All right. So we identify the two covering disks with the unit disk D2 in, or D, in the complex plane, and construct a bundle atlas with two maps, chi plus alpha comma beta, given by beta bar over alpha bar, just to make it, alpha divided by mod alpha as an element of D cross S1. So this element in the disk, this element in the circle, because we know that the bundle over the disks are just trivial. And chi minus alpha comma beta given by alpha divided by beta comma beta over mod beta as an element of, again, D cross S1. Oh, yeah, I'm getting there. Oh, hold on. I missed some conditions. This is for 0 less than equal to mod beta less than equal to mod alpha, and 0 less than mod alpha less than equal to 1. This is for the opposite case. And the reason we take this complex conjugate here is to make sure that on the intersection, which is the equator, both of these maps map to the same point in the total space in the S3. So that, we don't have the strip anymore. Our cover is now two disks with boundary and then the equator. That is the intersection. Just so that chi plus.
Points in the fibers over the equator gets projected to the same points on the boundary of the unit disk.
Oh,
the
yeah,
equator
yeah.
is represented locally by the same coordinates on the boundary of the disk D in both trivial positions.
Yeah, which is literally that. The restriction to the equator is same for both trivializations. All right. Oh, yes. The second one is chi minus. This is over D minus and this is over D plus. So both of these chi's are diffeomorphisms. They have to be because they're trivializations. And you can write their inverses. chi plus inverse of z comma e to the I psi is equal to e to the I psi over square root 1 plus mod z squared comma z e to the I psi over square root 1 plus mod z squared. And similarly, chi minus inverse of z e to the I psi is the opposite.
There should be computation. I think that's why.
Exercise.
The computation I plus inverse z conjugate.
Ah, yes, yes.
Actually,
You're right. Thanks.
on the previous step of alpha and beta,
Mhm.
we're not guaranteed that alpha and beta have the same phase, right?
No.
So those two things aren't equal on the equator. So the first term is fine, but the second term alpha over alpha magnitude is equal to beta magnitude, right?
Uh-huh.
But alpha and beta on the equator don't necessarily have the same phase.
No.
It's a unit of number. 1 over z bar is equal to z.
Yeah.
When z is unit, right? So
Yeah.
Oh, wait, so we're guaranteed. So on the equator, these two functions have to be exactly the same. So alpha and beta.
We just pick them so that they're the same. They don't have to be. So it's just easier.
So alpha and beta are literally equal here. So if alpha and beta have the same phase, then okay, we know that alpha and beta have the same magnitude on the equator, and so if they have the same phase on the equator, then alpha literally equals beta on the equator.
No, but they don't have the same phase.
Yeah, but the phases are.
Yeah.
So if they don't have the same phase, then why are we saying those two chi's are equal?
They turn out to be just plug into the point.
Yeah. So if alpha has phase theta 1 and beta has phase theta 2, this phase is going to be theta 1 minus theta 2.
Yeah, the first term is equal, of course, but the second term is not.
Oh, we don't. Wait, oh, sorry. So when I say restriction to C, I mean just the first component. The fibers can twist. That's why you have the transition functions. Yeah. Yeah.
So pi should be pi. Sure.
PR1. Yeah. All right. Okay. Any other questions? Cool. So we have these inverse maps, and of course, the equator is given by z is equal to e to the I phi in these coordinates, which gives us the clutching function, which is the transition function between coordinates on the equator. So let me call that tau plus tau minus plus. It's a transition function, so it acts on a point in the fiber on the sphere, on the equator. So it acts on e to the I psi. And its action on e to the I psi is given by projection onto the second component composed with chi minus, composed with.
So it should be tau minus plus of z, right? Taken at point z and then act.
Oh, yes, I forgot the z. Does this make sense? There's a transition function on the equator acting on the point of the fiber. So psi, as we saw, psi was an angular coordinate on the fiber. Z is a point in the intersection, which is on the equator. And naturally, transition functions are literally defined like this.
And the projection is just to pick out its action on the
Yeah. So this gives us, since z is equal to e to the I phi on the equator, this gives us tau minus plus of e to the I phi acting on e to the I, or just let me call this z. Just simplifying this, acting on e to the I psi gives us z inverse multiplied by e to the I psi. So it acts by multiplying z inverse. Okay, or equivalently, we can just ignore the e to the I side because this is multiplicative and write tau minus plus e to the I phi is equal to e to the minus I phi. So as a function on the intersection, it takes a point on the intersection and maps it to its opposite point, reverses the orientation. This transition, that's what this transition function does. And this is why we have the standard sign convention for the Chern number uh, of the Hopf bundle. Which we say is -1 because of this factor here.
And it doesn't, of course, it doesn't explain the convention because you just flip the sphere and did +1.
Exactly.
You replace the transition function with tau plus
Yeah.
Hopf bundle minus -1.
All right.
Huh?
We wanted to let them trivialize.
No, just
The tangent bundle has Chern number +2. Makes sense because the curvature of the sphere is positive and then you're giving it +2. But this bundle turns out to be relative to that.
If you reverse the orientation of the sphere, its curvature is minus, right?
wait, what?
Or, oh, no, right.
Curvature is a pseudoscalar would be bad news.
All right.
Wait, so Chern number specifically is wait, so it's only for the like this specific class of fibers.
As of now,
As of
now, we've only defined Chern numbers for fiber bundles over S2.
but it's more general.
General Chern numbers are for all complex bundles.
Okay.
Complex vector bundles.
Yeah.
But this is an example of a complex line bundle. But it's the only one we're really able to fully classify.
But it's over spheres.
This example.
But like in general.
I don't know over anything.
Over
Basically,
anything,
complex
yeah.
bundle.
I see. So,
Any complex bundle. Yeah. But it's just, so the classification theorem that we proved shows basically why in these fiber bundle business, it's important to be able to compute homotopy groups called V groups. Right, it's pi m minus 1. And that's in general very difficult. And moreover, what if our base manifold is not a sphere? Right? Then one transition function is not enough. And so it's not just one homotopy group of your G. It's a very complicated structure of functions mapping to G. So this is, you can see how it's not a very helpful tool for general classification of bundles.
So then in that case, the Chern number would just be whatever group element that your like characteristic group element of this thing.
It would be defined using like cohomology classes. It's literally like the dimension of some sort of cohomology class.
Those Chern numbers, will be related to also some homotopy classes of maps, only not into G, but into the classifying space of G. And there's going to be not one Chern number.
Is this group cohomology?
Yeah. And it's going to be not one Chern number, but it's going to be an infinite, in general, infinite sequence characteristic classes.
Classifying spaces.
It's just that the sphere is simple enough that one turns out to be enough to classify all bundles. Any concerns, wishes, complaints? So next time we'll dive into vector bundles then.
More simple stuff.
See, we went through a full circle. We started with changing vectors and we're going to do changing vectors.
When did we do that? Did we twist when we went full circle?
What's our turn number?
I want to go through David Pong's gauge theory notes with like this in my head.
Oh, that'll take a while. It will take a while.
We will do gauge theory.
Yeah.
I feel like this is enough to at least do something, right?
I mean, you need principal fiber bundles,
Yeah.
which we're not going to talk about.
Gauge theory is literally connection of principal bundles. That's all there is. It's gonna be a while till we get there.
But like, I feel like if you read because when you read the physics stuff, it's like take one example. Like it's easy enough to generalize from one example. Like,
I mean, going from this to principal fiber bundles is super easy.
Yeah.
Now that you know all of this.
so if I wanted to like phrase like just real basic like E and M, so I have been gauge field as the fiber space is actually like the E and B fields. Is that
I mean, you have your base space, real space, and over it you have the circle bundle, U1 base.
I see.
And the connection of the vector potential is values in the Lie algebra of the U1, which is off, right? Which is why the vector potential is the real value of 1. The connection is just a 1 form that takes values in the Lie algebra.
How does I'm confused about the terminology here. How does the gauge field give you a connection? Like, how does it give you a prescription for lifting curves?
Integrals of e to the a.
Oh, right.
Integrals
Of
e
course.
to the I a dx.
Right.
And that's how Differential comes. That's how the phase of wave functions. But even not very phase, just Aharonov bone phase. So
Yeah.
it's parallel transport in the connection.
Berry phase is not over like real space, it's over parameter space of the Hamiltonian.
So these fluxes, if you insert a flux, Aharonov bone flux, around some, and go in the loop around it, you pick up a phase that describes the holonomy of your the circle bundle or the line bundle.
so it's U1 over real space?
Over space time, in fact.
So yeah.
In geometric quantization, it's over phase.
Yeah,
Over that
phase space
space of like R.
of your system, whatever classical system you have. Go on. I need to run to office hours.
Phase space.
The open cir and the open circle. Oh, they're not diffeomorphic.
Supposedly it's not.
It's the corners.
How does it work? Can you show me?
I mean, basically, the idea is that.
P plus IP. Yeah, homomorphic.
How does that? How do you show it? I mean, basically, because isn't it just that you have to go?
Geometric quantization is super neat. Like to me, for the first time, to me, it really explained what.
This is a boundary point, so it has to map onto a boundary point. So
What all these Harman
As in, what's wrong with doing that? For example, like in angular coordinates, I mean, this is a square, this is a circle.
yeah, and it's
So you have your angle is theta. So your 45-degree angle just maps to this point here.
yeah, and so here, so as an example, so a function is a diffeomorphism. One sufficient condition, necessary and sufficient, or at least necessary condition is it maps smooth curves on smooth curves both ways, right?
Yeah, Yeah, smooth, yeah, okay.
Yeah, because the Jacobian, if you like, right? It maps tangent vectors onto tangent vectors. So if you take a manifold with boundary, you can have this curve, just that it falls along the boundary. That's smooth. This one is not. It's not differentiable there.
So in this case, what's wrong with mapping this point into this point?
Same thing, right? You take this curve here,